ladies and gentlemen. I'm Imansa from Indian National Academy of Engineering, your host for the 39th Foundation Day of Indian National Academy of Engineering.
May we request you to please put your mobiles on silent mode. Thank you. Good morning once again. On behalf of Mr. J.D. Patil, President, Indian National Academy of Engineering, we extend a very warm welcome to all our invited dignitaries, former presidents of INA, members of INA Governing Council, esteemed fellows, learned faculty members, young associates, members of INA, research scholars, and students to the 39th Foundation Day celebration of INA. The Indian National Academy of Engineering, established in 1987, is registered under the Societies Registration Act 1860 and is an autonomous professional body located at Technology Bhavan, New Delhi, and is dedicated to promoting engineering and technological excellence in India. It serves as a platform for engineers, technologists, and scientists to collaborate, innovate, and contribute to the national development. As the only engineering academy of the country, INA represents India at the International Council of Academies of Engineering and Technological Sciences, CATES. The academy was inaugurated by the then Prime Minister of India in April 1988, and over the past 39 years, this event has evolved into a landmark occasion. The Foundation Day is a moment to reflect on the INA's achievements, honor contributions to the field, and set new goals for addressing contemporary challenges in engineering and technology. It brings together fellows, young engineers, policymakers, and industry leaders to foster dialogue and inspire action towards technological process. The 2025 celebration of Foundation Day is at IIT Delhi, one of India's premier engineering institutions, underscores the event's stature and its alignment with academic and research excellence. The theme of 39th Foundation Day of INA is quantum technology, and the theme reflects the growing importance of quantum advancements in shaping the future of engineering and technological innovation. With this brief introduction, it is my privilege and pleasure to invite the esteemed dignitaries to the dais. May I request Mr. J.D. Patil, President, Indian National Academy of Engineering, to accompany the chief guest for today's function, Professor Abhay Karandikar, Secretary, Department of Science and Technology, Government of India, and the eminent speakers for today, Professor Susmita Surkole, Visiting Professor, Department of Computer Science, Ashoka University, and former Professor, Indian Statistical Institute, Kolkata, and Dr. L. Venkata Subramaniam, Head, IBM Quantum India. Ladies and gentlemen, please join me in expressing our appreciation to our chief guest and all the dignitaries with a resounding round of applause. Thank you. As a symbol of appreciation and reverence, I request Mr. J.D. Patil to welcome our chief guest, Professor Abhay Karandikar, by presenting a bouquet. I would now request Sir to please present a bouquet to esteemed speakers for the day, Professor Susmita Surkole, ma'am. Dr. L. Venkata Subramaniam, sir. Thank you. May I now request Mr. J.D. Patil, President, Indian National Academy of Engineering, to kindly commence the proceedings with the welcome address. Thank you, sir.
Good morning, and it's great to be here for this Foundation Day. 39 years, rather 38 years, and we have a 39th Foundation Day. As we just heard, the Prime Minister of the country felt it important to launch what we know as INAE. So this is the level of positioning this institution had when founded, and of course, over years, there's some amazing stellar work that has happened under the banner of INAE. This Foundation Day, the 39th, is exceptional and a very special one for a very simple reason that DST supported us from 95 to 2025. This is a long period of 3 decades, and in keeping with Government of India's decision, it was advised to INE that we become independent. As professionals, we can be more truthful to what we think is right than what the government would like to hear as a funded body. And this is a mandate which our leadership took. Professor Manna went through absolute hell of a time, but this is something which today we have been able to make some progress. INA today, obviously, roughly about 1/3 mark in terms of the corpus that we decided we'll create. And of course, there's some serious commitments in place for another 1/3. And hopefully, at some point in time, next 2 to 3 years, we'll be in a position to say that, yes, we have attained that complete autonomy to be able to manage on our own. I must say that Professor Karandikar has been an amazing support and enormous amount of strength for INA for what all he has been doing, formally, informally, and through all those support, we are where we are now. There have been a tradition that Foundation Day necessarily meant some food for thought, and some completely contemporary subject is then chosen, and then a couple of speakers we invite to speak. Just to tell you, post COVID, last 5 years, what did we do? The 35th Foundation Day was on April 21, and this was none other than Professor Sharma, Ashutosh Sharma, the then Secretary of DST. He was the chief guest, and the discussion was all about difference between science and engineering and the applications of science and applications of engineering. How does it differ and how does it really focus on specifics of science and engineering? We had at that point in time very specific select 4 talks. One was from DAE, one was from DRDO, one was from ISRO, and another from CSIR, in terms of now looking at the science and engineering aspects of what, as engineers, we need to be looking at. And this is essentially where the biggest technological achievements that have been achieved, notwithstanding COVID, during those last 2 years, that is precisely where the focus was. The 2022 event specifically talked about the opportunities and challenges of implementing the national education policy. This was an absolute hot thing in 22 that had just come in, and none other than Dr. Goel himself, who was the chief guest that time, and Professor Kasuri Rangan, who was the chairman of this NELP, was the one. And with him, we had a debate in terms of what does it really do, what is the genesis behind the NELP, and where to position it. The 37th Foundation Day was in 20th April 23. This was again at IIT, and Dr. Saraswat, the member of Niti Aayog, as we know, and the previous chairman of DRDO, he was present to specifically talk on some very specific subjects relating to advancements in technologies and energy side. The last Foundation Day, the 38th, on 22nd April 24, was again at IIT Delhi, and it was Dr. Goel who spoke that day. Dr. Kakodkar who spoke that day. Along with the Foundation Day, we had a specific event on the International Solar Alliance and what to do in terms of the renewables, how to change the complexion of this earth, and the focus entirely was renewables and what to do in terms of hydrogen economy. Today, of course, as we speak, as I mentioned, we are into a new era, and of course, this new era essentially means that as fellows, we need to do something different. Now, towards this, one very interesting initiative that we began this year, and which again, all credit to Dr. Manna, uh, there's a CSR initiative which is being funded by Infosys Foundation, and must tell you the magnitude of what this funding is. For the first 4 years, it's nearly 40 crores. And through 40 crores, the focus is to truly address the quality of engineering education in India. And towards this quality of engineering education, what needs to be done. And as a sort of a module, what is being targeted is for these 4 years, starting 2024-25, which is more or less already over, and we are talking about the next. As a part of this initiative, the 5 IITs, 5 disciplines of engineering, about 4,000 teachers, and the reason for mentoring teachers is essentially that the moment the teacher changes, he changes thousands of students. So the focus is on the tier 2, tier 3 colleges, all AICTE sort of certified colleges. And through AICTE's massive 7 lakh teachers is what the AICTE colleges employ. So 7 lakh teachers, 3,000 institutes is the spread. We are starting with not even 1% of that. But the beginning is in terms of taking this initiative forward. And I must say, our gratitude as an academy to Infosys and Shri Narayan Murthy, who actually said, we are all in corporates worried about the engineering education quality, and there's something that we can do, and we must plan and implement. So that's essentially where a very, very major initiative, which now is just about beginning. This year, in the month of June, the program will get launched. End of May, early June, it will get launched. The second very major part of INE, every year when we pick up our fellowship as well as the young fellows, there's enormous amount of showcasing of the work that they have done. Now this work remains only in the presentations, does not go anywhere beyond. So what we thought is we actually come out with a sort of a magazine which is essentially going to be carrying the amount of research that our young fellows or the young associates or the fellows or the members, which is yet another part which INA began this year, with that start actually showcasing in a very short kind of articles what exactly is happening in the research in the specific domains in the 10 sections that we have in engineering. Today, we will actually be seeing the launch of this as a sort of unveiling of the maiden magazine, a small magazine, 10 12 pages only, and hopefully it starts growing by showcasing what our own fellows would have done in terms of taking the research ahead. So the INA Tech Frontier happens to be launched today on the 39th Foundation Day. And I think that's the initiative which again will go quite some time in future, because even if we look at 50 articles every year, I think one is showcasing what our people have done. Second is to say it now gives a food for thought for others to start doing something. And the third is hopefully with this, more and more of our engineering research contributions that's happening in India start getting showcased. And of course, as INA would be extremely happy if any of the fellows or any of that quality of work is actually taken up or brought up to INA's notice, we'll publish it in that. I must acknowledge before I step down the enormous amount of support which we have seen from the fellowship during these hard years. Last 2 to 3 years have been not easy, and some of the amazing support. We have amazing solidarity our fellows have expressed towards the INA's continuation, and many of our fellows have given personal donations, and it was without any limit. Somebody wants to give 1,000 rupees, it's fine. It's only to say, I'm committed for INA's continuity, and this is something which has substantially been visible in the form of what people have done. The governing council support has been amazing in terms of repositioning of INE. And I think on the 39th Foundation Day, we can say we are again a new academy starting with new things to do, new ideas to come forward. And of course, we can only bank on our own fellows to actually say what we need to do. With that, let me rest and, of course, wish the entire academy, the fellowship, and the membership great times ahead. Thank you very much. Jai Hind.
Thank you for an inspiring welcome address. We are deeply honored to have your leadership guiding the vision and initiatives of INA. A new initiative is being taken by Indian National Academy of Engineering recently to publish an e-magazine on quarterly basis on engineering and technology updates pertaining to technical accomplishments of the fellows, young associates, strategic labs, major industries and R&D organizations and other eminent researchers. INE brings out a periodic e-newsletter which based news of the activities of the Academy, updates on awards and accolades of fellows, and has a section devoted to the major engineering and technological developments from across the world in major engineering disciplines as covered in the 10 engineering sections of INE. These write-ups are based on the internet survey, and it was expressed that there is a need to have a similar forum for researchers from across the country as well. It is envisaged that this initiative will provide a platform to the leading researchers in the country to showcase their latest achievements in engineering and technology that have brought them acclaim so as to give them a recognition and also inspire other professionals working in allied areas. The inaugural issue of the e-magazine features invited articles on quantum technology by leading researchers and professionals and their technological accomplishments in the recent past, which they would like to share with the engineering community at large, besides non-thematic articles contributed by INA Young Associates on their light themes. The inaugural issue of the e-magazine is based on the theme of quantum technology and is to be launched today. May I now request the dignitaries present on the stage to please release the e-magazine. This issue will be available on INE website from today. Thank you all the esteemed dignitaries for gracing the dais and adding immense value to the inaugural session. May now kindly respect all the respected dignitaries to please take their seats in the front row of the audience as we proceed to the next part of the program. We are about to delve into an incredibly exciting and cutting edge area of technology, quantum computing systems. The talk, titled Design Automation for Quantum Computing System, will be presented by eminent expert from academia, Professor Susmita Surkole, visiting professor, Department of Computer Science, Ashoka University, and former professor, Indian Statistical Institute, Kolkata. As the session chair, may I invite Professor Indranil Manna, immediate past president INE and Vice Chancellor of BIT Mesra, Ranchi, former Director IIT Kanpur, to please conduct the session. Thank you, sir. May I now request Professor Susmita Surkole to please come on the stage and inspire us with the first technical talk of the day. Thank you, ma'am.
Very good morning to all of you. We're really looking forward to listening to very eminent talks by very renowned experts in the field. And I've been asked to chair the session. The only qualification is one who knows nothing about quantum computing. So I have the pleasure and privilege of introducing the first speaker sitting next to me, Professor Susmita Surkole. She received her BTech honors degree in Electronics and Electrical Communications Engineering from the Indian Institute of Technology, Kharagpur, and the PhD degree in Computer Science and Engineering from Jadavpur University. She has been a faculty member in the Advanced Computing and Microelectronics Unit of the Indian Statistical Institute, Kolkata, since 1999. Recently superannuated, she is now a visiting professor of computer science at Ashoka University. During 93 through 99, she was a reader at the Department of Computer Science Engineering of Jadavpur University, and earlier she was a postdoctoral fellow at University of Nebraska-Lincoln, a research assistant at the Laboratory for Computer Science in Massachusetts Institute of Technology, MIT. She was also on sabbatical at the University of Bremen, Germany, Princeton University, and Intel Corporation. Her research contributions are on design automation for VLSI, physical design, fault modeling and testing, and synthesis of quantum computers. She has co-authored several technical papers in leading international journals and refereed conference proceedings, a chapter in the handbook on algorithms for VLSI, physical design automation, co-edited 3 books. She has served on the committees of several international conferences in various roles, including General Chair and Technical Program Chair. She was on the editorial board of a number of top-tier journals. She was a distinguished visitor of IEEE Computer Society India and is a fellow of Indian National Science Academy and certainly of Indian National Academy of Engineering, a senior member of IEEE. Among other awards, she was the recipient of the President's Gold Medal and Distinguished Alumnus Award at IIT Kharagpur, International Excellence Fellowship of the Karlsruhe Institute of Technology, IBM Faculty Award, and Women in Technology Leadership from VLSI Society of India. All of us are aware of the IIT and the dreadful IIT JEE. Suffice to say that nowhere in the world we have an example of success rate of 1 in 200. Maybe during her time it was 1 in 100. But nevertheless, to be the President's Gold Medalist, which is the topper of the batch in the entire IIT across the departments. And please remember, there was no computer science engineering in her time. So that's the kind of profile Dr. Surkole carries. We certainly are looking forward to listening to you, ma'am. With your permission,
Yes. Yes.
Do I have a hello? Is it on?
Yeah.
Yeah. Thank you, Professor Manna, for the very kind and long introduction. And thank you for inviting me today to this very special occasion. Am I audible? Yes, okay. So the title of my talk is Design Automation for Quantum Computing Systems. I have been, from my background in electronics and then computer science, I have been working on design automation for VLSI systems for more than almost close to 45 years. And it was about 15, 20 years ago when logic synthesis of quantum computers came about. And then with a student of mine, I said, why not look at the issues, how they're different from digital circuits. So the agenda is that for this audience here, I'll just give a very brief introduction to what quantum computing is about. And then being an engineer, a computer scientist and an engineer, how do we map quantum algorithms to the systems? So there's a term called quantum compilation, which I'll try to explain very briefly in this short span of time. And then what are the challenges that we have in building these? Lest I forget, I have a list of collaborators, many of them my former students. And as you can see, the speaker here, the next speaker, Dr. Subramaniam, his group at IBM was collaborating with us, which led to very fruitful research. So what are the major drivers of quantum computing? There are two main things which led to this spurt in developing quantum computers. One is the algorithmic limitations. The classical computers, in the next slide, I'll try to explain what are the differences. The classical computers have a limitation on the computational time, the complexity and the space required, despite all the data centers and the cloud computing and also the supercomputers. There are problems which would need very large amount of time to solve them, and particularly problems which are related to nature, from physics or chemistry, particularly quantum chemistry. And the other driver is the hardware limitations. So the IC technology, the semiconductor technology or nanotechnology, as you know, the features, the transistors are getting smaller and smaller to the tune of, currently there are transistors to the tune of 3 nanometers. And for your reference, there are some, real life dimensions like diameter of human hair, the red blood cell and flu virus, just to give you an idea how small the transistors are. And within this space of 2.5 centimeter by 2.5 centimeter chip, all of us have at least one chip in our pocket, there are about billions of transistors working at gigahertz range. Now, you know from basic physics that whenever a system changes state, there is an energy dissipation associated with it. And therefore, if you have, when in the ICs, in the digital circuits, the way it functions is by switching from ones and zeros, and the transistors are switching. So a lot of heat is dissipated, and that's a major issue in data centers and in all computers. So, and the fact that they are switching so fast at gigahertz level, as well as sitting very close to each other. So that was kind of a very hard challenge for IC designers. Now, it turned out that quantum computers have some solutions to these two specific points here. The figure on the top left is Charles Babbage's electromechanical computer. The one in the middle is the picture of a wafer, a silicon wafer. The little squares are each dies which form the chips. And we are on to quantum computing over here. So how will quantum computing change our lives before I get into what are the specifics of it? Particularly for optimization and simulation. The hard problems that you have. So we expect to have a lot of improvement in drug and material design with quantum computing, and of course AI. So pharmaceuticals and chemical research is going to have a great boost when we have these quantum computers available. Finance modeling, climate change and climate prediction, these are very burning problems today. Cybersecurity and travel planning, autonomous vehicle design, and even in astronomy, you have large amount of data which you need to quickly analyze and come to conclusions. And also social sciences such as election prediction, which has so many parameters that you need a lot of compute power to do that. A little bit of history. We had the first model of computing by Alan Turing in 1936. And it was way later, about 50 years later, Richard Feynman he's a Nobel laureate in physics, and he has been thinking about the physics of computation quite a bit. He has published on that. So it was at a seminar, a conference in MIT, and it just so happened that I was a graduate student at MIT at that point, and being a great fan of Feynman, I had gone to listen to his talk. And in that talk, he had mentioned that there's a lot of room in the bottom, and in order to simulate quantum chemistry, you need to make use of quantum mechanics. At that point of time, not being a physicist, it didn't really strike me that much. But very soon after, in 1985, a theoretical physicist in Cambridge, David Deutsch, actually proved that computationally, you do get, for certain problems, an exponential amount of speed up. But that was sort of I would say, an engineered problem. It's a valid problem related to Boolean logic. A few years later, Peter Shor, a mathematician, he proposed an algorithm for factoring a large integer. And why was that a landmark? Because before that, the main public key cryptography system, the RSA, invented by Rivest, Shamin, and Adelman in the late '79, was the basis for e-commerce and all kinds of cryptographic protocols that you have. And the basis of the success of this protocol is because it's very easy to multiply two integers, but very difficult to find the factors. Remember, in our primary school, we would keep dividing by the prime numbers starting from 2, 3, 5, and so on to get the factors and find the greatest common factor and so on for two numbers. But Peter Shor showed that to factor that in classical time, I mean, it was already known that in classical computing, it would need exponential amount of time to factorize a large integer. And that's why RSA was based on that, strength. But Peter Shor showed that with a quantum algorithm, you can solve it in polynomial time. And that made everybody sit up that, oh, what's going to happen to all this cryptography? What if somebody builds a quantum computing? And there were people who started looking at how to build quantum computings to take advantage of this huge amount of power that quantum algorithms seem to be providing. Okay, there were 2 Nobel Prizes in physics in a span of a decade, which actually were to experimental physicists to show that the basis for quantum algorithms can actually be realized. So what's the difference between classical and quantum computing? To be very honest, all devices, all matter occurs, in that quantum mechanics is working. But at a macro scale, we don't get to see those differences. So in a classical computing system, the smallest unit of information is called a bit, and in digital system, in a discrete system, it can be in one of the 2 states, that is either a 0 or a 1. And mind you, only one of the 2 states at any instant of time. Whereas in quantum computing, the unit of information is called a qubit, and that can simultaneously be in the 2 what are known as basis states, and with respect to that, as you can see on the top, that the state of a quantum, the quantum state, can be expressed as a linear combination of the two basis states. And there are the factors there, A and B, as you see in the top right, are related to the fact that the quantum system is an isolated system. And the moment you measure, it collapses to one of the two basis states. And those factors of superposition gives you the probability with which you will see the state that the factor is associated with. Typically, this can be visualized as a unit sphere, and as you can see, this combination can be any vector in the unit sphere on the surface of the unit sphere, which is a linear combination of that. And for the sake of computation or simulation, the zero ket on the north pole, one of the basis vectors, is represented by a column vector, and the one ket also by a column vector. Now, in classical computing, there's no superposition, whereas in quantum computing, there's a superposition of states, which actually gives you the computational power, and it can increase in exponential time. For example, if you have n qubits, you would have n bits would represent 2 to the n different numbers, but only one at a time. Whereas in quantum, because you can have superposition of all the 2 to the n, that gives you a provision for massive parallelism. There is a phenomenon called entanglement. So quantum computing is based on 3 important phenomena in quantum mechanics: superposition, entanglement, and interference, which we don't see at the macro scale. The other point is reversibility, which means that very little power is spent on computing which is reversible. But there are some bottlenecks, which is that you cannot copy a quantum state. Why? Because to copy, you have to read and then write. Now, the reading means measuring, and the moment you measure, it collapses to one of the two states, and therefore you don't get the original state that was in isolation. So that's a major difference in which you have to keep in mind when you're designing the quantum circuits. And the other challenge is it's very fragile because there's no perfect vacuum. So therefore, there is an interaction with the environment, and that would lead to high error rates. And of course, till now, most of the technology that we have needs ultra cold temperatures, not room temperatures yet. But it's found that it's very good for complex simulation and optimization. For mundane tasks, our classical computers are good enough. So the reversibility, I think in the interest of time, I will skip all this. Just to show you that you can represent this with linear algebra in terms of matrices and vectors and do the simulation to find out what is happening. Now, here we saw only ones and zeros. So one might say that what's the difference with classical where you have binary? But in quantum, we have more than that, and we can have these complex numbers as well. This doesn't work. So we have what are known as 1 qubit rotation gates, as you see over there. And that sphere, if you remember, you have x, y, z axis, and you can rotate about any of those axes by a certain amount to get a different vector within that sphere. So that means if you apply one of those rotation operations or gates on the current state, which is again represented as a vector, by that amount theta, that vector is going to be moved or rotated. Okay. Then you have some other fault tolerant gates. I don't have time to go into the details of all of them. These are 1 qubit for one quantum system. You apply these operations. And how do you operate? Okay, I'll get to that in a minute. Before that, I would like to point out to the last one on the top, on the bottom right, which is the H gate or the Hadamard gate. And I will show you that that is the key to superposition of equal superposition of the basis states. These are for 1 qubit. Then you have 2 qubit gates. The important ones are the C0 and the swap gates. And you can have a large number of gates. So what is a quantum circuit? You have qubits, and you have these gates. So the first gate that you have is a 2-qubit C0 gate. The X is is equivalent to the NOT gate. The Z is again, and the cross there is the swap gate for 2 qubits. Now I must tell you that unlike electronic circuits or digital circuits, where you have the gates and the output of the gate feeds to another gate through a wire. So when you draw a circuit, you have the elements and the connections, which are wires. So in VLSI design, you have to deal with that. But in quantum circuit, you don't have wires. What do you have? In electronic circuits, you don't look at the electrons or holes, which are carriers of current or which is making the circuit work. You can see if you, pull out your chip from the mobile and look at it through the microscope, you can actually see the transistors and the wires. So the gates and the wires. In quantum, you don't have any wires. So then what are those lines? So they are depicting time. And then how do the gate operations happen? There are no transistors. Gate operations happen by applying electromagnetic field or pulses on the isolated quantum system. So you have to monitor all that, and therefore the cost metrics are somewhat different. So basically you keep on applying these, and the corresponding operation has this matrix through which you can run your simulator. So superposition, as you can see, that if you multiply the matrix for the Hadamard gate to one of the two basis states, you'll get equal superposition. Okay. Whereas if you have C0, you have something which is entanglement, and entanglement is very important for quantum cryptography, which means that if 2 qubits are entangled and if you put them physically apart, if you perform an operation on one of the qubits, the other one also has a correlation, and you can predict what's going on over there. So this sort of summarizes. I would point you for the students to look at these website, Quantum Algorithm Zoo, which lists all the quantum algorithms so far, and they are categorized. Many of them have exponential speed up over classical algorithms. Some of them have super polynomial speed up, and then you have approximation algorithms as well. Okay. I don't know whether I'll have time for this. I think I'll skip. How much more time? 5 to 10 minutes? 5, okay. So this is a very fascinating algorithm, and I always like to share this with the students. This was this factorization algorithm, as you can see. And the idea is very simple. So it comes from a number theoretic relation that suppose I want to factorize the number 21. So I choose a number which is less than that and which does not share any factor with it, okay? But then you will notice that if you raise the small number x to powers and perform what is known as modulo 21, which means that you divide by 21 and whatever is the remainder is the answer. So 2 to the power modulo 21, 2 to the power 4 is 16. So 16 modulo 21 is 16. But if you go to 2 to the power 5, which is 32, if you divide by 21, you have a remainder of 11. Okay, so that's the way you go on. But the nice thing is you can prove that after a few powers, it becomes 1 again. So which means that this function is periodic. And if you know the period, in this case it's 6, then, and if you find out 2 to the power 6 by 2 modulo 21, which is 8, then if you find the greatest common divisor of 8 minus 1 and 8 plus 1 with the number given, you get 2 factors. And the reason this works is very simple. It's something which we had learned in our grade school, because y is whatever x r by 2 modulo n, and so y square minus 1 is actually modulo n, it divides evenly. Therefore, the y plus 1 and y minus 1 has to share a factor with n. And so if you take the GCD, you will get the factors of n. Finding GCD in classical computer is polynomial time. So why weren't we able to do this before? The reason is finding R. And Shor gave an algorithm which instead of exponential time in classical time, in polynomial time we could find that R. Okay. I'm at this point, I'll just point out one thing, that is quantum computing, by the way, is probabilistic. Because remember, when we measure to get the output, there is a certain non-zero probability of getting an output state which is not the correct one. The purpose of quantum algorithm is making use of interference to enhance the probability of the state corresponding to the correct output and diminish by destructive interference to reduce the probability of the states corresponding to the wrong output. Okay, so that's how quantum algorithms are designed. So to build them, you need computer scientists to design these algorithms, you need the physicists to come up with the technology, and for people like us, engineers, we need to have synthesis methodologies. And there are certain criteria we need: scalability, initializability, measurement, and because of this fragile nature, we have to make the gate operation time and the whole circuit operate within a certain small amount of time, otherwise the state itself is going to change by itself. Testing and control, even though it's classical, we need to reduce the precision error. So these are some, early days you had nuclear magnetic resonance, but now you have quantum based on superconductors and quantum dots and other things. And this is a report of 2023 which shows where we are, and we still have a long way to go to be able to do, I think I'll leave Venkat to talk about this roadmap of IBM, where we are. So we did some work on design automation, and this is this quantum circuits synthesis flow, where you have, in a quantum algorithm, you have some classical functions and quantum functions, which you convert to both of them to reversible and put them together. And then based on the particular technology, I haven't told you about the technology yet, you need to again do some mapping and optimization and finally place them. Okay, so the leading technologies for quantum are based on, as you see, quantum dots, superconducting, ion traps, neutral atoms, and photonics. And you have to keep in mind, not all types of operations are primitive to all the technology. So that's where we need a little bit of optimization. Only some primitive operations which are available depending on the particular technology, your cost will depend on that. I'll skip all this just to show you this, that some of them, the ones which are primitive, has a cost of number of operations is 1, but for the others you have to express them as logic identities and the cost goes up. So therefore, the cost, you have to keep that in mind when you do the optimization of the quantum circuit at the logic level, keeping the technology in mind and also the quantum error correction that's needed. And we found that in our system, by these optimization, we could reduce, I think it's not visible very well, but we could reduce the amount of quantum resources, which is the number of operations, quite a bit. Okay, and for physical mapping, as I'll just show with an example before I stop, we want the 2-qubit operations for the 2 qubits to be close to each other, because that electromagnetic pulse, if they're far away, is not going to work properly. So if it depends on where the qubits are mapped. You have a fixed in the topology in which the qubits have been connected or placed. And so in your circuit, you have to map those qubits onto the particular technology and particular device that you are having. And if they are not close by, you have to do a sequence of swap operations to bring them close by. So if you do a mapping incorrectly, you might end up doing a lot of swap operations, but I would like to have an algorithm to do the mapping well so that you minimize the number of swap operations, and we propose some of this in polynomial time. These are hard problems, and Now the problem is that, all this while we were assuming that we would have lots of qubits, but in this noisy intermediate scale quantum device era, the NISQ era, we have just a few qubits where we can't even have quantum error correction, because for quantum error correction you need a lot more encode each logical qubit into a number of physical qubits, so you need a lot more qubits. So in the meantime, people have proposed what is known as, so as you can see in quantum computer, there's a lot more error and error correction is needed. In the simulator, you may have very good, but in the actual device, because of noise, you would have different things. So I'll skip all this. You need error syndrome decoders, and we have used machine learning based techniques to find out what the error was so that we can correct the error, and some other ways of so what we have now is hybrid quantum classical algorithms. You have some classical optimizer feeding some parameters to the quantum system, and then you do so, you measure and check whether it's good, otherwise you kind of iterate. And for some of the NP-complete problems, it was shown that the approximation is pretty good. What we did was, because there's noise, and the noise is not even uniform, not all the qubits have the same amount of noise profile, not all the gate operations have the same amount of noise profile, and it's not static, it varies every day, every moment. So it's on a daily basis, you have to keep that in mind to do. So the 2-qubit operations are very noisy, so our goal was to reduce the number of 2 qubits, and we were able to do that. There were certain conditions based on which you can do that, and because of that we could reduce. So we could do quite a bit of reduction, and if you have fewer qubits, the noise and the error rate goes down much less. Then also you have a lot of circuits and a few amount of devices, so which circuit has to be mapped onto the cloud. For that also we gave a solution based on ILP, and with that, keeping error correction in mind, we could do quite a bit of reduction and in better fidelity. We have the National Quantum Mission, as everybody knows, and there are 4 thematic hubs. There are institutes and, who are working on quantum computing, communication, sensing, metrology, and materials. So this is my last slide for parting remarks. The synthesis part, the algorithm and the automation part, there are a lot of things, still a lot of things to do, better algorithms for logic level optimization, physical mapping, error models. We do have a number of efficient transpilers, which are software development kits, like Qiskit from IBM, SERC from Google, TCAT from Cambridge, Quill from Rigetti, and a number of others. But there are issues where, as the technology progresses, that has to be taken into account. Quantum controllers, a lot of work needs to be done, and verification and testing, even IP protection, and of course, quantum computing and AI. Okay, can quantum computing help AI? We have used AI to help us design better quantum computers. We want real algorithms for real applications, and we would like quantum devices at a much lower, much higher temperature, so that the amount of power required to keep the quantum computers at low temperature is lower, because the actual computation requires very little power, but to keep the device in the cryostat, that is an issue. So the future of computing, as we can see, we won't have quantum computers on our desktops. We won't use it for adding and mundane tasks, but we would have supercomputing with certain tasks for which we have a lot of speed up. It's kind of a co-processing by quantum computers. The interface, of course, has to be designed very carefully. Thank you, and sorry for running over time. It was a very rushed overview of the problems that exist, and I'd be happy to take any questions.
Fascinating talk and a great revelation. So if you like to ask one question or
Yeah, I think, I'm going to ask a very practical question. What low temperatures, at what low temperatures?
Millikelvin.
Pardon?
Millikelvin.
Millikelvin.
Almost close to zero.
Close to zero. Okay.
So,
that's
absolute zero.
for the stability of the quantum system.
Yes.
The other question I had is one of the major concerns that in operating large data centers is actually the energy consumption.
Yes.
So do you have a ratio, I mean, is there an estimate that whether the quantum computing would reduce the energy consumption for the same volume of computing? I mean, today we have a certain number.
Yeah. So we don't have quantum computers to handle the same volume of computing yet.
Yeah.
We would have some kind of, estimation. And I think Venkat here is a better person to answer, and I'm
Okay,
sure
maybe
he
in
will.
his talk he can cover.
Yeah, from IBM, they are the ones who are actually working with the technology,
Right,
and the numbers would be more realistic than
Right.
from an academician who sort of, take their numbers and then go on with the algorithm device or the system.
And the final question.
Yes.
See, quantum computing as an idea is quite old actually, it's not very new. So when is it going to achieve a realization that you see it's in supercomputing, for
I
example?
think I had a slide which I sort of
Timeline kind of thing.
Yeah.
When we will see.
So let me see if I can quickly get to it.
I think I missed that maybe. All right.
Just before this.
We have miles to go.
No, I think if they have any.
Yeah,
comment on that?
yeah. So here, as you can see, in 2025, I think Venkat is a better person to answer. In 2024, we already have a system, but it's not available to everybody for us to use yet because the error rates have to be tackled. And the hope is by the end of 2025, we have so many. But as you can see from this, we need at least about 10 to the power 4 or 10,000 or maybe to the tune of 50,000 qubits, physical qubits, to be able to do some meaningful operation. And I might tell you that ion trap has a very low error rate, but its decoherence time is also very low, a few nanoseconds. So you have to complete all the gate operations in sequence within that time. Otherwise, there is an error in the equation. Yeah.
There was a question.
I can't hear you. I think your mic is not turned on.
When you have done this quantum error correction, because IBM update its whole system and topology also, then in what topology respect you calculate your quantum error like regarding this?
Yeah, quantum error is kind of inherent in the technology, in the device that has been fabricated. And the error correcting code is a different thing. So new error correcting codes are being looked into, which is, as you have rightly guessed, that it is kind of related, not directly, but then fact that just because we don't have all-to-all connections, if we had that, then any QECC would have worked. But since we don't have that, we would have to look at some new QECC, and research is going on over there. So
I think we have to close this interaction. What I've personally found most amazing is that generally in the computer science community, they talk only of binaries and numbers. I think it's easier for, I'm sure like me, many others in the audience to connect. Thank you very much.
Thank you.
Indeed an excellent talk.
Thank you very much, ma'am, for the truly enlightening and thought-provoking talk. On behalf of everyone present, I express our heartfelt gratitude for taking the time to share your expertise and wisdom. May I now request Professor Indranil Manna, chair of the session, to kindly give a memento to the distinguished speaker of the session, Professor Susmita Surkole. Thank you. We now move on to the second technical talk of the day, where we have the privilege of exploring another crucial aspect of rapidly evolving world of quantum computing. The topic of the talk is Quantum Decade India's, and it will be presented by a very eminent expert from industry, Dr. L. Venkata Subramaniam, the head of IBM Quantum India. May I request Dr. L. Venkata Subramaniam to please come on the dais. As the session chair, may I invite Dr. Sanak Mishra, former President INAE, member of Governing Board, Steel Research and Technology Mission of India, formerly Managing Director, Rourkela Steel Plant, and member of the Board of Steel Authority of India, to please conduct this session. Please.
Yeah, it is my privilege to introduce Dr. L. Venkata Subramaniam. He is at the IBM Quantum India Limited and earned his PhD from IIT Delhi in 1999. Recognized as an IBM master inventor, he has been granted 38 patents and has published over 150 research papers that have gathered over 3,300 citations. Recently, his book, Quantum Nation, hit the bestseller lists in India and on Amazon. Currently, as the head of IBM Quantum India, his mission is to help establish India as a leader in artificial intelligence and quantum computing technologies. So we are all eagerly waiting to hear your lecture. I'll go down and... Thank you, sir. Please.
Good morning. It's a pleasure to be here. I studied from IIT Delhi and it's a great honor. I've attended many lectures from here. When Professor Shantanu Chaudhary invited me, I couldn't believe it that I'm being invited here. So it's a great honor. Thank you so much. So when neural networks was being offered for the first time in IIT Delhi by Dr. Shantanu Chaudhary, I was a student there and I barely passed. Okay, the project saved me. So yes, so thank you so much. So today I'm going to give you an overview of what is quantum and how it is going to shape the future and especially India's role in it. Okay, so that's what this talk is about. It's about where India can, contribute in this area. So quantum computing today, we all write our programs, C, C++, Java, Python, whatever language you know, and then what happens? A compiler compiles it into machine code. The machine code is ma'am said, the basic unit of information on your classical computer is zeros and ones. So the compiler compiles your Java, Python, C, C++ code into machine code, zeros and ones. And that gets operated, that gets implemented on the classical computer. On the quantum computer, what changes? Nothing changes. This remains the same. Same Python, same C, Java, whatever you want, you can write in that. The compiler or the transpiler converts it into a new set of languages. As ma'am said, it utilizes the power of quantum mechanics, utilizes superposition, entanglement and interference to do the computation. So today, the entry barrier into quantum computing, at least for somebody who is in computer science and who knows programming, is very, very simple. All you need to do is write the same code in Python, but this time you have to use the principles of quantum mechanics, and that's what's different here. So as we all know, supercomputers have existed for a while, and Moore's law, every 18 months compute power doubles. That's why you have your mobile phone today, after 2 years you have to buy a new mobile phone, because better camera, faster apps, everything runs faster. So this used to be the most powerful supercomputer, and now it's maybe number 10 or 12 or whatever it is. So Moore's law has been happening for several decades now, still continuing. Compute power is still doubling every 18 months. But then there are still some problems which we cannot solve, and that's where quantum computing comes in. One example, caffeine, small molecule of nature. Can we simulate it on a computer? Well, if you tried, it would require 10 to the power 48 bits. That's like 1/10 the number of atoms on Earth. That's a fraction of a second. The states in the caffeine molecule, where are the electrons, what are they doing, all of that modeling, if you wanted to do, it's going to take you 10 to the power 48 bits. You can continue Moore's law for several more years and it's still not going to be able to do it. Okay, and here comes quantum. All you require to do this is 160 qubits. That's all, 160 qubits. Another example, ma'am mentioned Shor's law, Shor's algorithm. All our encryption today is based on the fact that you cannot factorize large numbers into prime factors. Prime factor of 19, 3 into 3. Prime factor of 15, 3 into 5. But prime factor of a 2048 bit integer takes 8 billion years, 8 billion years. And that's why we use it in our encryption today. But the same problem, 2048 bit integer, which takes 8 billion, Shor's algorithm shows that it will be done in 8 hours. Exponential speed up on a task like factorization. So I gave you two examples now. One is molecular simulation, another is factorization, another, learning, AI. We all know how is AI done. See examples, learn from that, build a model. Cat problem. What is the cat problem? As a child, how many cats did you have to see before you recognized a cat? 1, 2, maybe, right? How many cats does AI require today? 10,000. Cat from this side, occluded cat, kali billi, gori billi, all sorts of billis before AI can recognize the same cat. What is the problem? The problem is same data, but the way you model it, the way you infer it is very, very different, inefficient. And hence, what's the problem? This cat is the problem because today every time an LLM comes up, on this side, what comes up? A power station. So the first decree that the US government did on 20th Jan after he took over was he declared an emergency in the US on energy emergency. Because the future of technology is driven by power. But that's where quantum also comes in. Can we take it from 10,000 closer to the 1? That's the big question before quantum, and we are already seeing some evidence that it's possible that you can move that cat problem, you can try and solve this cat problem using quantum AI. So these are 3 examples I gave you, but I'll not go into this. We all know fundamental unit of computation is zeros and ones. Ma'am just explained superposition, entanglement, interference. But is the future going to be only quantum? No. Multiplication, hundreds of times faster on your classical computer. On your mobile phone, laptop, it's much faster. Hence, the future is CPUs, GPUs and QPUs working together. And that has already entered. We have entered this era. On your laptop, on your mobile phone, you have CPU. In the data center, you have GPUs today. Very soon, you will also have QPUs. In fact, QPUs are already there. So the future is where your job gets broken up into pieces, which multiplication go to CPU, AI go to GPU, quantum go to QPU, and that future has already begun. People have already started solving some of these problems using this combination of QPUs, CPUs and GPUs. So, is there a Moore's law in quantum? Yes, we are seeing that too. 2016, 5 qubits. 2024, 156 qubits. 2033, 1 lakh qubits. So that same scaling is happening in quantum too. So in the very near future, you're going to start seeing, the hardware in fact has already reached a point where you can start building algorithms and start running code on your quantum computers. Error correction is going to come 2029 in the IBM roadmap, but remember, is error correction entirely necessary? In your classical computers, error correction came in the year 1950. Much before that, classical computers were useful in World War, in nuclear research and all of that. And that brings us to this question. There are two terms I want you to go back with. The first term is quantum advantage. What is quantum advantage? Quantum advantage is where a quantum computer takes a problem and solves it much, much faster, much, much more efficiently compared to a classical computer. That's quantum advantage. Have we reached that point yet? We have not reached it. When are we going to reach it? Well, according to IBM, we are going to reach it next year, 2026. In 2026, you are going to see a problem solved, which is a business problem, not a theoretical problem like random sampling or something, but an actual business or scientific problem which you see solved on a quantum computer and which you cannot on a classical computer. And that is not very far, 2025, 2026. Now the question is, who is going to solve it? Where is quantum advantage going to come from? Any thoughts? Okay, next year quantum advantage is going to come, and keep this question in mind, where is it going to come from? Who's going to bring it? So take examples, internet came in the year 1983. When did internet become useful? In the late 90s, when Netscape came up with the browser. Before the browser, we didn't know how to use internet. We all bought PCs but did not buy internet connections in the 90s. Before Google, we didn't know how to search data. It was all lying there on the net. We didn't know how to search. So the utility of the internet came only after people showed algorithms and applications like Google search, like Netscape browser. Without them, the internet was sitting in the lab. Same way, AI, we've been hearing it for several decades now, but it became useful and it came to our desktops very recently. Same way, quantum has been there for a while, but this is the time for it to come to mass usage. And that, as I said, is the year 2026, when we believe that's going to happen. And who's going to do it? That's the big question. And the answer is, where is the talent today? On our IBM systems, the power users are all from India. India is where we are seeing the talent. India is the place where all the kids from second tier, third tier, we aren't even teaching them quantum in their colleges, but they are going and learning, self-learning, and they are using these quantum computers online, on the cloud for free, and that maximum usage is happening out of India. So at least for us in IBM, we are seeing that the talent is sitting here in India. So the question of who's going to achieve quantum advantage first, I think the answer, the natural answer has to be, it has to be India that has to achieve quantum advantage first. And to that, I know sir will follow me, so I'll not go into any of this in much detail, but there is the National Quantum Mission, and the goal here is to ensure that, so there are all these hubs, IIT Delhi is one, there are these startups that are getting supported, there are these quantum technology courses which are coming up. The primary goal of this is to ensure that India becomes the leader in quantum technologies within this decade. There are 34 countries with national quantum missions of their own today. 34, more than any other technology. There is no other technology which has so many countries saying I have a national mission on quantum or even AI doesn't have so many countries. Okay. The primary reason is, all the defense agencies, the advisors, the technologists, all of them are saying to their governments that the country which takes the lead here will have several decades of economic dominance over Earth. That's the primary reason. That's it. It's very simple. And hence, the goal here is that in quantum, given all the talent that we have, this is the time for us to make sure that, we solve some of these tough problems and get that lead. There are some very interesting results already coming out of India. All of you know last year's Nobel Prize in physics was for AI. In chemistry also it was for AI. It was for protein structure prediction. And but AI, it needs seen data. You learn from sequences. When you see an unseen structure, it's not very good at predicting. So that's what this work we did with IIT Madras was around trying to predict unseen structures of proteins. Why is protein so important? So a small lesson in medical things. So we have 25,000 proteins in our body. One protein shapes like this, another protein is like this, another protein like this. There are multiple types of proteins. When a protein loses shape, that's disease. Molecules fix this, that's medicine. Medicine fixes the proteins. The goal is to find these medical molecules which will go and fix the proteins in the body. That's what disease fixing is all about. That's what medicine is about. That's what drug discovery is about. I told you caffeine molecule. Remember, small molecule, we can't even model that on a classical computer. We can't structure the molecule, how the protein is going to fold. So all of that is what quantum computers, because they are naturally aligned to do these kind of things. The same properties that this molecule follows, the quantum computer also follows. So it's a very natural way of solving some of these problems for the quantum computer. So, and this one used 114 qubits. That's a very, very interesting number. Okay, why? Because you've now crossed 100 qubits, beyond which we are seeing you cannot simulate on a supercomputer. It is not possible anymore to simulate. You can simulate up to 30 qubits, 40 qubits and all of that, but you cross 60, 70, 80, 100, you are into a completely new regime, completely new. You cannot do it on a classical computer. Computing for the first time has branched. There are two types of computers. One is your classical computer, your mobile phone, laptop, supercomputer, all of these which use the fundamental unit of information as 0 and 1. Then there is this new kind of computer which uses the qubits for its computation. And this qubit you cannot simulate using the zeros and ones, as ma'am said. Feynman, 1981, that was the whole point he made, that you need quantum computers to be able to simulate these properties of nature, which you cannot do using zeros and ones. And hence, a lot of these things that we are seeing, this is again, energy operator landscapes. How do you calculate the energy states in a molecule or an electron, which is very important in drug discovery, in new materials, electric vehicles, all of these areas. Okay, so I'll not go into a lot of this, but a lot of people are now looking at how do you create hybrid approaches where you solve the CAT problem, basically the AI problem, where you're looking at representing, modeling and inferring from your data much more efficiently so that it's energy efficient and also more accurate. So this is work where people did, my team, they worked on spatial tissue modeling using a hybrid technique of quantum classical. So I'll sort of, okay, there are many applications which people are now beginning to look at. Lots of them across India also. Many people are looking at many things. So for example, fraud detection, all of us use UPI today, the biggest number of transactions in the world. You put together China, US, France, Germany, and it still doesn't add up to that. But the problem is 0.01% of the people using it are dishonest, trying to create fraud. How do you find that in real time? It's impossible for the best supercomputers today. And the hope is that quantum computers will be able to solve problems like these. So across various sectors, across areas, three types of problems: simulating nature, mathematics, processing data with complex structure, and search and optimization. These are the three kinds of broad problems that people are solving. So I'll end here with a very simple thing for all of us. You all know your laptop, mobile phone, any compute. Today the computers, 5 countries control the supply chain: China, US, Taiwan, South Korea, Japan. Whether it is the hardware, whether it is the software, these are the 5 countries which control the global supply chain for any kind of computers today. Now, the future, as we are discussing, is quantum. Who's going to control the supply chain for quantum in the future? And the whole goal of the National Quantum Mission is to make sure that India gets into, in the next 10 years, we should be in there controlling the supply chain for this. So one very important point which I want to make today, the processor on your computers, how much of the total cost do you think that is? It's about 10 to 15% of the total cost. For any mature technology, the processor cost is going to stop there, 15% max. So even in quantum, even though today the focus is on the processor, eventually it is going to settle down at 10 to 15% of the total cost of everything, the hardware, software, everything. So there's a huge opportunity here that we as a country can take upon right now. We can, control the supply chain. There are multiple parts there, as ma'am said. Today, the cost per qubit is about $10,000. In future, it has to come down at least 100x. 100x in the next 10 years. Otherwise, this technology is not going anywhere. So there is huge opportunity for us, India, as part of the National Quantum Mission, as part of our industry here, startups, to bring down that component cost, to bring down the cost of these quantum computers from $10,000 to at least $100 per qubit, and also the size. Ma'am mentioned the room temperature. To me, I think even more than room temperature, the size. If you are able to compress the whole thing, even today your GPUs are sitting in the data centers. We don't need the QPUs to sit on our desktops. but we do need them to become scalable, to have thousands of qubits at an affordable cost, and for that the whole supply chain needs to be more efficient, not just the processor. And I think that's what the National Quantum Mission's goal has been, to sort of ensure that we are in the middle of all of this. So I'll stop there. Thank you so much.
Thank you. Is on, yeah. Thank you, Dr. Subramaniam, for a very brilliant lecture. I think an exposition of what is going to come. And let's give them a big hand for this. I think we can take a couple of questions, queries, only questions. Yeah, please.
Sure. There's a lot of challenge in terms of the hardware. The logic part you explained. What do you think are the biggest? Is it material synthesis or as integration, or because temperature problem you just made a mention is not the hardest hurdle. So what are the biggest hardware hurdles?
Yes, sir. So, yeah, so a lot of the hardware hurdles, as I said, is to bring down the cost and the size. You know, as I mentioned, today it's $10,000 per qubit, needs to come down at least 100x. Okay, and of course, a major part of that is the qubit, you know, the processor itself, but also, you know, the cryogenics, the wiring inside, the microwave, the amplifiers. So a lot of work needs to be done by the electrical engineers, the, you know, the control system engineers and all of them before the whole package, you know, becomes much more efficient, scalable. Today you order a quantum computer from IBM, it takes us about 4 to 5 months to put it together. At that rate you are not scaling at all, you are not doing any scaling, you know, in the near future. So a lot of research needs to be done and a lot of hard engineering, you know, because the wiring, for example, we all do wiring, you know, no big deal, but this is cryogenic wiring now. So you need to make sure that the wire conducts at that temperature, does all the things that are needed, is flexible, because you need those wires to go across the fridge and all of that. So at least in IBM we believe a lot of hard engineering is what is now the requirement. A lot of the science has been done, the physicists have done their part. Now it's for the electrical engineers, the computer scientists, the mechanical engineers to start jumping in, and the main goal is that 100x reduction in cost and size.
So you talk in your book, you talked about various startups such as QU Labs and Artificial Brain, and like we do know that there's still some time before we have a wide range of business applications of quantum computers. So like most of these startups are surviving on funding primarily. Could you comment about the revenue strategies that these startups are employing and what sort of revenue strategies being employed by IBM Quantum?
Okay, so IBM Quantum reached 1 billion in revenue last year, December. Okay, so there is a lot of money to be made, of course. This year, IBM strategy is to spread that 1 billion across startups, as you said. So there is a marketplace that we have created where any startup can come and start putting its applications and things. And just like your Google marketplace or Apple store, users can come and start using them, right? So that's the whole purpose of this marketplace, where startups can create these applications which they can then, for example, banks or whatever, can come and start using. Today the money is in algorithms. Okay, that's where the money is. The low hanging fruit is algorithms, because a lot of the banks, the pharma companies, all of them want to get ready. because they're seeing the promise of quantum and they're thinking, okay, next 5 years, 7 years, 10 years, if IBM is saying quantum advantage is happening in 2026, how do we get ready? And I see a lot of algorithm startups already creating some sort of revenue pipelines, and that marketplace is one. But I think it's much harder for the hardware startups, especially in India. But the 8 that got funded by DST and NQM, I'm seeing a lot of them now getting chased by VCs. There are VCs in Bangalore with $800 to $1 billion India specific tech funds. Okay, they are looking for youngsters like you to start startups so that they can come and give you the money. Okay, honestly, they are there. And these 8 startups are now getting chased by these VCs. So there is a lot of money out there in the system which is waiting for young people from India to come and give their ideas and scale them out and become world beaters, as I said, because there is a huge opportunity.
Sir, in the last lecture, ma'am said that sometime quantum computer gives a wrong result. If we forget about the error part, as a principle of a quantum computer, that is a superposition principle, it's not give wrong result, because every superposition states whichever one of the collapse in system particularly after measurement, it's a real state, it's a reality. Each superposition state is the reality. Then how can quantum computer sometime gives a wrong result? I am not talking about the error part.
Yeah, so see, the problem with quantum computers is, number one, the coherence time. You know, any state you put it into, it stays there for a few milliseconds, okay, and you got to do all your computation within that time, okay. And even the states that you put it into, you are not always able to put it into the proper states, and the measurements are also not always accurate, okay, and that's where the error comes from. And that's what I said, by 2029 we will have error corrected. Today what we use is called error mitigation. What is error mitigation? Error mitigation is those earphones which you have, noise cancelling earphones. What do? They measure the ambient noise here, and then they create a filter to filter out that noise and amplify what noise, what music you have, right? So error mitigation today does the same thing. What it does is it measures the way in which the errors are propagating within your qubits, okay, and in your gates, and it tries to amplify and mitigate some of those errors, right? So that's what is going, current computers use that, but in future error mitigation, the good thing about it is it doesn't need extra qubits, but it needs extra runs. So you need more time, more number of shots to run your program, and then it does an averaging on top. With error correction, what will happen is you don't need to have multiple shots, but you need to have extra qubits. So there is a trade-off between mitigation and error correction, okay. And yes, the measurement error and the gate errors are what is causing this error which ma'am mentioned.
Before I wrap up, I would like to have a response from you from something I'm going to say.
Yes, sir.
You know, several years ago, there is one more question. Okay, just let me finish this and come back to you. Several years ago, you know, I heard a lecture by Dr. Praveen Chaudhary, who was that time the head of R&D at IBM, and he talked about this future of quantum computing, and I think he said that the main issue would be, you know, achieving the low temperatures of, you know, as he said, below 1 degree Kelvin, close to 0 degrees Kelvin. But he said the main problem would be the thermal stability of that core quantum computing molecules, or whatever you want to call them. Yes. So it still remains, right?
It still remains, but now there's a roadmap which says 2029 it gets solved. Okay.
It gets sorted out.
It gets sorted out. Okay. Yeah. So that's where we are at this point.
So please go ahead. Yeah. Praveen Chaudhary was also from IIT Kharagpur, like our distinguished speaker, Professor Sur Kole. He was also from IIT Kharagpur.
Hello, sir. Thank you so much for such an insightful talk. I had mainly two questions. The first one being, I think a lot of points in your book and as well today were made on the capability, the natural capability of the component of the quantum computers to mimic the nature, the nature. As also in one of your examples of the cat, that it will be able to identify uh, the cats in one or two images, just like a human brain does. Do you think that quantum computing in the future will be able to mimic the human brain? And if yes, then what is the timeline that you think will be by when we'll be able to achieve this? My second question being, I think a very major point made by you was like why AI is mainstream right now, and I think and as you rightly said, it's because the common person can use it, um, and that's why. So, what do you think will be a problem in the future that the quantum computing will be able to solve, which will be beneficial for a common person not having an expertise in quantum computing, just like we are saying in the AI hype right now?
Yeah, I'll start with the second question. Actually, see, when Tim Berners-Lee came up with the World Wide Web in 1983, he had no clue we'll have Ola, we'll have Amazon, we'll have Flipkart, or we'll be using UPI to do all our transactions. Usually what happens is when the technology comes and it reaches a point where uh, you know, young people like you come into the picture, that's where it really takes off. Okay, I'll give you one simple example. Amazon came in the US in 1994. Okay, Jeff Bezos that time was 30 years old. When did a similar startup come to India? After 15 years. Why? Because internet penetration was not there in India. 25-year-old Bansals came up with, implemented the same thing in India, but they had to wait about 13-14 years before they could do it, because you know, the internet penetration was so low in the country that even if you started a app like this, nobody would be using it. But I think the point really is that, you know, people who are early into the technology will only see extensions of the old things. I will be saying, oh, drug discovery will solve it. But you, the young people, are the ones who are going to actually think up the new things and solve those problems. Okay, so it would be very easy for me to say, oh, we'll do drug discovery, this one. But honestly, we don't even see 5% of what's really going to happen in the future. Sorry, your first, oh, brain mimicking. Okay, so I don't know if we'll ever mimic the brain, because all we eat is, you know, our roti, and then it powers the whole brain to do that cat thing. Okay, to do the same cat, you need thousands of servers sitting somewhere, and you need power stations. Now, tech companies are buying nuclear power stations in the US. Okay, so are we ever going to be as efficient as the brain? I don't know. I have no clue. It will certainly bring it closer. Yes. Thank you, sir. Yes.
Thank you very much, sir, for that truly enlightening and thought provoking talk. It's been an absolute privilege to listen and learn from you. May I now request Dr. Mishra, chair of the session, to kindly give the memento to distinguished speaker of the session. Thank you, sir. Thank you. Ladies and gentlemen, it is now time for a very special moment in today's program, the keynote address to be delivered by none other than our esteemed chief guest, Professor Abhay Karandikar, Secretary of the Department of Science and Technology, Government of India, who is also a member of Mission Governing Board, National Quantum Mission. May I now request Dr. P.S. Goyal, former President INAE, former Chairperson, National Innovation Foundation, India, Honorary Distinguished Professor, ISRO Headquarters, and Raja Ramana Chair Visiting Professor, formerly Secretary Ministry of Earth Sciences and Chairman, Earth Commission, and Director, ISRO Satellite Center, to kindly come on the dais and chair the session.
Good morning to you all. After two very interesting and illuminating talk, we have once again a distinguished person, Secretary of Department of Science and Technology, Professor Abhay Karandikar, who will be speaking about again the same topic as a keynote address. He is currently Secretary of Department of Science and Technology, and he was in IIT Kanpur for a long time, up to 2018 to 2023. He is a very accomplished person, educator, innovator, and also now administrator. He has a very high record of establishing himself as a scientist, as an engineer, and his impact of research is seen in a very broadband access to which he is a formation of so-called Fugal 5G working group in IEEE standards. His research has a profound impact on starting of the activities of the global IEEE standards, which is of course a very unique contribution. Well, his group has also made pioneering contributions to towards 6G architecture in ITU. 6G is something, and we are talking about the future, and of course, we are probably as good as the world in terms of the advanced computing techniques. He's spearheaded the national effort in setting up telecom standard development society in India called TSDSI, India's standards body for telecom, and he's the founder member and former chair of TSDSI. He's also member of Telecom Regulatory Authority of India during January 2018 to 2021. He's a very accomplished person, and we are very happy that he is there with us. I request Professor Karandikar to give the keynote address.
Thank you very much. I think after two very enlightening talk on quantum, you will see some change. I'm not going to speak on quantum. I thought it may be appropriate to sort of speak on how, we are currently through the missions, as was mentioned, National Quantum Mission, we are transforming the scientific landscape of the country. And I will just give you, some insights into what the government of India is doing and what has been its impact and what really lies in future. Now, just to give you some data point, I think in the recent years we have seen a significant progress in the scientific output. One is that in terms of publications in science and engineering only, we are now number 3. In 2022-23, we had about 2 lakh publications. These are all Scopus indexed publications, so there is some sort of a measure of quality. We are having now, almost 6th in terms of number of patents being filed by resident Indians. Okay, so I think that is sort of important. And also in science and engineering, we are now number 3 in terms of producing the PhDs graduates. So I think in these respects, I should say that we have done, really well in the last few years. In terms of startups, as all of you know that India has emerged as the third largest startup ecosystem in the world. We have about now 1,60,000 startups which are registered. But more important is in 2016 we had 11 startups which were unicorns. Unicorns means a valuation more than $1 billion US. In 2025 we have 118 startups which have valuations more than $1 billion. And approximately the total combined valuations of these 118 startups is in the range of 400 billion US dollars. So I think this is very, very significant. There has been a significant funding that has come in the form of venture capital. For example, in the last 3 years, we have about 80 billion US dollars in the form of venture capital funding that has come. We have about 1,59,000 startups. It's always a question that gets asked. How many of them are deep techs? It is our estimates, it is Department of Science and Technology's estimates that is about 10 to 15,000 startups are real deep tech startups. 4,000 of them came out only in the last 5 years, and they garnered about 8 billion US dollars of the VC funding. So I think we are actually doing pretty well in the innovation landscape. Now, if you look at some think tank reports, so there was this report on Australian Strategy Policy Institute report in August 2024, which are tracking the critical technologies based upon the high impact publications only, not based upon the technology or the products. This is just based upon the share of the high impact publications. Interestingly, China is leading in 57 of the 64 critical technologies, just in terms of the publications. Okay, and US is only leading in 7, but India ranks within 5 in 45 of the 64 critical technologies. And these are some of the technologies in which we have a significant share. For example, if you look at biofuels, biological manufacturing, and more interestingly, quantum sensing and quantum cryptography, we are either number 3 or number 4 just based upon the publications. But obviously there is a gap between translating this research into the technology development or the products, because clearly we are not number 2 in biofuel technology or on biological manufacturing or even in composite materials. So actually contrary to popular perceptions, our share of high impact publication has really increased, and it is thanks to the premier institutions such as IITs and ISCA and TIFR that we have done sort of very well in the last few years. In fact, as a director of IIT Kanpur and also as a faculty in IIT Bombay, I can tell you that the research in IITs is at all-time high than what used to be there like 30 or 40 years ago. And this is often not recognized, but the research is really currently all-time high. What we have failed is in translating this research into deployable products and technologies. So therefore, clearly the engineering aspect has been missing in terms of bridging the gap between high impact academic research and the technology development. Yeah. Now, we have been, thinking in the government of what should be the focus or the R&D roadmap. And clearly, I think we divide the problems, into three parts, which are actually the global challenges, but also the challenges which are affecting our country and society. One is, of course, the sustainability and fragility, and this is either in the form of climate change or in the form of geopolitical shift that is happening, and therefore causing these technological challenges either through cyber attacks or bioweapons. The third one is resource constraint, and these resource constraints are coming up because of the increasing population in the world. We are having constraints on food and water, on minerals, on critical mineral scarcity, etc. So there is, of course, strain on the resources, the food, water, minerals, and so on. And because of the longevity in the life, we are also having, strains in the healthcare system. And in fact, India, which is a young country now in 2047, when we are talking of Viksit Bharat, is obviously going to be an aging society. And therefore, really we need to think on technologies which will take care of an aging society. Transforming lifestyles are also having challenges in terms of transportations, housing, pollutions, digital connectivity, and of course, the challenge of artificial intelligence. So these are really, three buckets of the challenges, and our goal is to really develop technological solutions which can actually address these challenges. And whether they are in the form of renewable energy, which is green hydrogen, e-mobility, or whether in the form of precision agriculture or biomanufacturing, or even going into the deep sea mining for addressing the resource constraint problems, or medical devices, healthcare, and so on. Basically, the strategy is to develop a tech ecosystem which is resilient, which is innovative, which is addressing the socio-economic welfare, and which is giving our country a competitive advantage. So resilience, innovation, socio-economic welfare, and competitive, which is basically addressing RISC, the future risks. Okay, and that is, I can tell you that this is really some kind of a roadmap to address the global and societal challenges to achieve the goal of a developed economy or a Viksit Bharat. Now, to do this, we need certain structural changes, and the government has taken some actions, and I will speak only about few of them because we don't have some time. One is there are some institutional reforms and strategic initiatives are needed. Again, these initiatives can be divided into two forms. One is what we need at structural levels, whether they are at the institutional level or strategic level. And I will talk about three major structural initiatives that the government has taken. One is in the form of Anusandhan National Research Foundation. Second one is a 1 lakh crore research development and innovation fund that has been announced in this budget. And third was certain institutional and governance reforms that the government has taken, and I will elaborate on that. The second bucket is to take certain sectoral initiatives, and these are to address some of the global challenges and also the societal challenges that I mentioned. These are national missions on quantum or cyber physical, national mission on electric mobility, semiconductors, national missions on biomanufacturing, medical technology, national missions on weather, blue economy, and on the space technologies. So basically these are sectoral and focus areas, and I will give a brief on some of these in sort of today's discussion. Now, the first institutional reform that we did is the Anusandhan National Research Foundation, and the genesis of the Anusandhan National Research Foundation was in the National Education Policy, and it was envisaged in the National Education Policy that the research and innovation at our educational institutions, particularly in the state public universities, is at a very nascent stage, and these universities have a significant potential. Therefore, we need a concerted efforts to catalyze the quality research in the education systems, and therefore the NEP 2020 has envisioned the establishment of a National Research Foundation. The ANRF Act was notified on February 2024, and the erstwhile Science and Engineering Research Board was therefore dissolved. And after that, the first meeting of the governing board happened on September 10th, 2024, and in this meeting, 4 major strategic interventions of the ANRF has been planned. Of course, under these interventions, there will be large number of R&D programs, initiatives and missions, but these are primarily 4 major strategic initiatives. One is to boost the research capabilities in the universities, and as I mentioned, that this is an important aspect why the ANRF was conceived as one of the major recommendations of the National Education Policy. Now, under this, we recently launched a program called PAIR, which was a hub and spoke framework for uplifting the science and technology ecosystem. Since the research in state public universities is still at a nascent stage, it was thought appropriate that established top tier institutions can work as the mentors, and then they can have the spoke institutions as the state public universities. In the first phase, we have already chosen 7 such spoke institutions which will be mentoring about 45 state public universities, and we have already announced a commitment of almost 700 to 800 crores for this. So this is sort of one program that has been launched. The second program is to do the mission mode research and invest in the translational research, and this is clearly, as we can see, while we have the potential to do a very high impact research publishing in high impact journals, but we clearly need a gap of translating that research into the commercializable research, and therefore we are emphasizing on this translational research and the mission mode research. We will again soon have the specific programs in this, including programs which National Science Foundation has, for example, small business research initiatives, investment in the startups, setting up translational research centers, setting up centers of excellence in premier academic institutions, and so on. The third one is, apart from the fact, on the one hand, while we improve the research ecosystem in the state public universities, we need to continue to invest in the institutions which are already doing well and have the potential to go to the global level. And that initiatives will form the center of excellence, particularly in premier institutions where we can aspire to be in the top ranked institutions in some of our key sectors. And finally, of course, to focus it on the capacity building, and that capacity building can be in the form of early career grant or advanced research grants or PM professorships, national postdoctoral fellowships, and so on. So these are primary, therefore, 4 strategic interventions that ANRF will do. Under each strategic interventions, there will be some large number of R&D programs that will get rolled out. We have initiated few programs, but now the new CEO of ANRF has joined full time. I was only acting as the additional charge for the last 1 year, and with this new CEO, we are hoping that in this year 25-26, we will have almost all the programs of the ANRF which will get rolled out, both in translational research and also the basic and applied research, focusing on both state public universities as well as on the setting up centers of excellence in the premier institutions. Now, coming to some of our focus areas where we have launched the mission mode program, as was mentioned in the previous two lectures, the quantum is clearly one of the focus areas which Department of Science and Technology is leading, the National Quantum Mission. And under that mission, we have four verticals: computing, communications, sensing, and materials and devices. We have already set up four thematic hubs: IISc Bangalore in quantum computing, IIT Madras and CDOT in quantum communications, IIT Bombay quantum sensing, and IIT Delhi in quantum materials and devices. And again, in this mission, the R&D focus is to develop indigenous technologies and systems in all these areas. Primary goal is to develop the capability in the country to not only be useful to develop technologies which are which will be deployable in our country, but also become globally competitive. And as a part of the National Quantum Mission, as Dr. Venkat already mentioned, we have already funded 8 startups. Almost 70 crore rupees have been invested in these 8 startups, and we hope that in the next few years we will be investing about 300 to 400 crores again in the startups of the quantum area. The cyber physical system is again a mission which DST has been running since 2019. And as a part of that mission, it has established 25 technology innovation hubs across India in almost all premier academic institutions. But however, the major thing that we are now doing is 4 of them we are now upgrading to the technology translational research parks, focusing on these areas, AI, ML, robotics, cyber security, Internet of Things, big data, healthcare, agriculture, water, manufacturing, and so on. In AI, our sister ministry, Ministry of Electronics and Information Technology, is having an India AI mission, and that AI mission will facilitate the researchers and access to AI compute infrastructure of more than 10,000 GPUs. India AI mission is also funding sector specific foundational model, and in fact, as a part of our national mission on cyber physical system, we have already funding a large language model for the Indian languages at a consortium led by IIT Bombay and called Bharat Gen. In fact, DST has given significant funding to this consortium. In biomanufacturing, I think there is a great thrust on the biomanufacturing. Again, our sister department, Department of Biotechnology, had come out with a Bio E3 policy, and under that Bio E3 policy, the objective is to create an ecosystem of academia and industry for the technology and innovations. Under this Bio E3 policy, the plan is to establish the bio foundries and biomanufacturing hubs, and soon the DBT will be funding both academia and industry to set up these bio foundries in the area of bio-based chemicals or lab-grown foods, which could be alternative to, for example, the animal products, precision biotherapeutics, and so on. Currently, I think the bioeconomy in the last 5 years has grown significantly. Today, it is about 150 billion US dollars, and with this Bio E3 policy, we would like to expand our bioeconomy to grow to 300 billion US dollars in the next 3 years, positioning India as a global leader in the bioeconomy. So in the last few years itself, the economy grown from nowhere to almost 150 billion US dollars, and there are large number of very innovative startups which are working on precision biotherapeutics, bio-based chemicals and lab-grown foods, which have a potential of really disrupting the bio industry in the country. In health and medical technologies, there are various initiatives by different departments like Department of Health Research, Indian Council of Medical Research, or Department of Biotechnology, and DST, and the Ministry of Ayush. In fact, the ICMR has already launched a MedTech Mitra program for hand-holding the startups in the medical technologies. In the Department of Science and Technology, we will soon be launching a mission on the medical devices and technology, a national mission on the medical devices and technology. Of course, the Department of Biotechnology, DST and ICMR have been supporting research projects in the area of gene therapy and advanced robotics. Finally, I think we are working with the Ministry of Ayush to integrate the Ayush into the modern healthcare systems by using the modern scientific tools. Now finally, I would like to mention about the recent announcement in the budget which was done of setting up a research development innovation fund. Now, as I mentioned that in the last few years, even though we have received $80 billion VC funding, only about 4 to 5 billion US dollars has been in the deep tech. That is that typically the deep tech startups, they have a long gestation period. They may require 5 to 6 years for the technology to mature from let's say a TRL 3-4 level to a TRL 7 to 9 level. For example, let's say a technology like a gene therapy or a drug discovery requires about 6 to 7 years of periods, and obviously the private investors are averse to taking such risk. Okay, and as a result, therefore, we need some mechanism of providing a patient capital to the deep tech startups, and also the private sectors which have typically in India have shied away from investing in the core cutting edge R&D. As all of you know that in India, as a percentage of the GDP, private sector is spending only about 35% of the total investment that we are doing, which itself is very low, is about 0.7% of the GDP, but private sector contribution is only about 30 to 35%, while the government is spending about 65 to 70%. But in all advanced countries where there is a significant spend on the gross expenditure on R&D as a percentage of the GDP, almost 70 to 80% is coming from the private sector. For example, in countries such as South Korea, Israel, US, and where the gross expenditure on R&D is about 3 to 4%, the 70% is coming from the private sector. So therefore, we thought that in order to catalyze the private sector investment, the government has set up a research development and innovation fund. This will be a 1 lakh crore fund, and this will be for investment in the private sector, not in the academic institutions, not in IITs and ISC or other research labs, but investment in the private sector with an objective to foster R&D and innovation to develop a product-driven economy and achieve the goal of the strategic autonomy. This fund will provide the long-term concessional financing for the startups, for corporates, and for focused research organizations which are in the private sector engaging in R&D in some of the critical and emerging sectors, which are important. And as I mentioned already, that technology focus areas which we have identified in order to achieve the goal of a developed economy. The fund is supposed to therefore promote the product-led businesses and the domestic capability in critical and emerging technology. So, sorry, I don't have details of this, but just let me know that this fund is being anchored in the Department of Science and Technology. Already in this budget, 20,000 crore has been allocated against the DST, and the fund will have a two-tier structure. We are in the process of setting up a special purpose fund as a part of the DST, and we will identify the second level fund managers. The second level fund managers could be the alternate investment funds, or they could be institutions such as BIRAC, or already existing institutions like TDB of DST, and some funds which I know, for example, IIT Bombay's incubator is already setting up a deep tech fund. Indian Institute of Science Bangalore has already set up a deep tech fund. As you know that these incubators are operating as Section 8 companies, and now they have set up an alternate investment fund. I know that IISc's fund is already registered with SEBI, IIT Bombay is in the process of doing, which and there are several other deep tech funds have come. This fund, Research Development and Innovation Fund, can fund in fund of funds also, and also can, through the second level fund managers, do retail investments in both deep tech startups and direct large corporates as well. But the key is that these R&D projects should be in the critical and emerging technology. All the three kinds of financial instruments will be used. That is a long-term debt at a very low interest rate, but of 10 to 15 years, or an equity, or an hybrid of all the three. So currently in the Department of Science and Technology, we are in the process of setting up this special purpose fund mechanism, which will then be used for identifying the second level fund managers, which will do the investment in the sectors. We are hoping that by an investment of about 1 lakh crore, it will catalyze 10x investment from the private sector, and also will mitigate some of the risks which are private VCs are facing in terms of investing in the deep tech areas. So finally, I should say that the Government of India has implemented several institutional and sectoral reforms across the sectors, and I should say that I was actually somewhat fortunate to operationalize two of the key areas, which is Anusandhan National Research Foundation and National Quantum Mission. And also we are now in the process of operationalizing the Research Development and Innovation Fund. These are three major institutional reforms that the government has done. And the goal is, of course, to build a world-class S&T ecosystem, doing strategic investments in these areas. Finally, I think strengthening human capital and R&D infrastructure is very, very important. Traditionally, the Department of Science and Technology has already been involved. And finally, I think, as I mentioned, through deep tech area, accelerating the disruptive technology, whether it is AI or quantum or semiconductors or green energy or telecom, is extremely important to achieve the technological sovereignty. And finally, for a sustainable future, we need innovations to address the climate change, the resource constraint, and the resource constraints are really the food, water, and materials. Because if you have to live as a materialistic human being, it is really very, very important to address the resource constraint challenges, the climate challenges, and the growing living lifestyle challenges, whether they are in the urban or rural, in terms of basic necessities of transportation, housing, and pollutions, and while ensuring the inclusive growth. I did not talk about certain structural reforms that we are already doing towards what we call as the ease of doing science and research. There also, we have taken now several initiatives, and I'm also happy to say that I'm in the forefront of driving some of those initiatives. Finally, I think our vision is to emerge as a future-ready and self-reliant global leader, and any developed economy can only be based on science, technology, and innovation. And in that context, therefore, all of us have a big role to play. And as I already mentioned, that while we are done reasonably well in scientific innovations, we still need engineering excellence and deep tech innovations. And I think in that context, since INA is focusing on harnessing and nurturing engineering excellence, the task is much more than ever before. So thank you very much for inviting me for this talk. I'll be happy to take. Any questions?
Please raise hands. Yeah, Mr. How is it?
Yeah, I have a question which is of a very general nature. See, looking at it at a very macro view, you know, the first 50 years after independence, India, you can say, was busy on building a higher education ecosystem, and you can say an S&T ecosystem. So maybe till the late 90s, that was so. Now, when, you know, some time back, I had a discussion with one of the countries in Asia only, which is a leader, you can say, in innovation and technology. So we talked about the spending on R&D, that they spend about 3.5% on R&D. And of course, I lamented that in our country, you know, it's probably less than 1%. R&D I'm talking about. But, you know, he made a very interesting comment. He said that the expenditure of 3.5%, there is also a basis in that country. I will not name that because he said that is based on what economic impact that R&D is going to make. In India, I think we still are not thinking, haven't started thinking about what economic impact S&T is making. You know, you talked about the startups. You know, most of the unicorns, they are in the service sector. Of course, they use a very advanced level of IT technology. There's no doubt about that. But that's growing, and it's a very welcome thing. But I would like to hear from you. Is there any thinking that we need to assess what economic impact S&T spending by the government is making? Are there any studies or any because unless that is done, it will be very difficult to convince the taxpayers that we'll spend 3% on R&D.
No. I think let me just make this distinction of spending the taxpayers' money and spending this 3% of the GDP. There is I think many people have this confusion, because anyway we do only 20% of the spend only of the GDP. So I think so you can only have that much. Spending taxpayers' money is different. As a percentage of the GDP is the spend by everyone, that is by you, me, private sectors, industry, everyone. So I think there is a big difference between how much out of the total revenue of the taxpayers' money the government is spending. So if you want to know that, percentage is very high because you know, just to give you an idea, this budget, for example, the R&D expenditure is about 1,20,000 crores. So which is almost maybe about 10% of the total revenue that the government is getting. So that is not, so the percentage of the GDP, and these questions are therefore intertwined, because the technologically driven economy, if it is not growing, then obviously the percentage of that GDP is definitely less. And that has to come from the industry and the economic activity and in the private sectors. That cannot come alone by the government pumping in money, because the government has the limited spending from the, and therefore these private sector industry. So since you talked about the educational system, but let me just give you about the industry. Most of the industry revolutions in the country has either been, you know, when the IT revolution happened, that was in the mostly in the service sectors, or most of the industries in the country which were manufacturing were importing the technology and then developing the products here. Core technology R&D was not being done here. Now, unless you do that, the core R&D, the industry was not investing in the R&D. The industry was investing mostly in importing the technology. So, one of the reasons therefore of the RDI fund of the 1 lakh crore fund is that this will spur 1 lakh crore is not just sufficient, but we are hoping that once it takes some initial risks, it will encourage the private sector to bring in maybe 20 lakh crores and or 30 lakhs crores, and then the percentage of the GDP will also improve and the economic impact will also be substantially higher. And I think that is.
But would you, for example, this what you mentioned, that this new fund that is created, would you build into that a component to make an assessment of what impact it will make?
I think this is a very good question, and this is exactly. I think we were debating about this RDI fund. That what is the KPI for this fund? The KPI for this fund is not that government invested because this fund was, as Honorable Finance Minister's budget announcement was, that it is a 50-year concessional loan that the DST will be giving to the special purpose fund. So the idea therefore is not for the government, that government has given 1 lakh crore and government gets back 2 lakh crores. That is not the KPI. The KPI is exactly what you are saying, that by investment of this fund, how much economic impact it has created in the tech-driven economy. So I think that is clearly one KPI.
Thank you.
Just one comment I'd like to make in this context. See, the return is not a very common factor across the all R&D. It depends on what aspect you are touching. I'll just give you only one example. There is a small service provided by the Ministry of Earth Science. We call it PFZ, Potential Fishing Zone. Shailesh Nayak actually requested a study to be conducted. What is the impact of that? Our total expenditure from Ministry of Earth Science is hardly 30-40 crore per year. Rest, of course, satellite cost that is coming separately. But the study showed that the fuel saving, diesel saving by 4 lakh fishermen itself was coming to 50,000 crore per year. So it depends impact on sector to sector. There is no common answer for that. No. Yeah, some people are doing. I'll give you more examples later. But this is something. We have few things I can give example. Yes, sir. Go ahead.
Thanks for a very, I would say, an excellent presentation. And I think it gives a very positive feeling when you leave this auditorium that a lot of interesting things are happening. Okay, all the segments that you mentioned and the amount of rupees and dollars that you mentioned. My concern and the question is, particularly from the academic side, industry is a separate domain altogether. The ease of doing research. You are well aware of it. You were at IIT Bombay, then IIT Kanpur. I think today, if one wants to talk to researchers at these leading institutions that you mentioned, they all feel very handicapped. In fact, people are unable to spend the money which is given by DST. Okay, so any comment that you have that how we can change this particular scenario, because otherwise these beautiful schemes will not fructify the way you have envisioned it.
No, I think this is a very good question, and we have taken this initiative. I think ease of doing research. We have identified several pain points, which includes in the fund flow mechanism. Whether it is through the treasury single accounts or otherwise. Then it includes certain relaxations in the GFR. It also includes certain conditions in terms of the procurement processes. So all those things we have identified. We have taken a comprehensive solutions for this, and I am discussing this with let me just tell you, at the highest level, this has been discussed, and I'm hopeful that in the next 6 to 8 months some results will be seen. Regarding this RDI fund, already there is a provision that the fund shall make its own liberalized financial rules. So in the DST, we are also now thinking of setting up As far as the ANRF is there, the act of the ANRF provides that the central government shall make financial rules for the ANRF. We have already constituted a committee under the chairmanship of the IISc director, Professor Rangarajan, and IIM director, IIM Bangalore director, and there are a couple of other members from ISRO and DRDO and from finance, which is framing the financial rules for the ANRF, which will be hopefully different from the GFR and more liberalized, because the ANRF Act provides that. So first, that financial rules, once it comes and gets approved, will be rolled out in the ANRF funding. We are hoping that over the course of time, those rules can be adopted for other scientific ministries. So I think that is, I should say, is a work in progress.
Yeah, so I had a small question here. It's a three-pronged question, so just bear with me. First is the mindset issue. Let's look at the industry in the first place. If you look at the industry, if they had two options in terms of a homegrown technology vis-a-vis the technology they have to import from Germany, where would they prefer, let us say, 5 years from now? We know the historical background. So having said that, let me come to the research institutes. The professors and the research academia have one single KPI. That is, how many papers have they published? Now, if we look at as to how many of their research work is at an MVP stage, I did a small 60,000 feet above the ground because I had just retired that time, so thought I will just contribute a little bit here or there. I found just not more than 2% of the research within one of the IITs, I don't want to name, were at the MVP stage. Third, very recently, I decided, let me just see if I can foster the research from academia to the industry. It is very strange kind of a thing. Some of the best research that is done, unlike what was published in the recent news items and all that, is available, but neither the academia is willing to take it to the industry, nor is the industry willing to. So this is two. The third part, going back, there were tax rebates which were given to the R&D in the industry. I don't know how much it fructifies. This fund, if at all it is given to the industry, my bigger worry is that it will be a free cash that would be available without any outcome-based absorption that is taken care of. Yeah. So I don't know whether I've confused enough, but pardon my throwing up this question, which in this forum may not be right. Yeah.
No. I think let me just answer all the three questions. So first is, I think, about the academia publishing research and not translating. So I think this is I should say this is a bit unfair on the academia, because let me just tell you, because I also from academics. Academics all over the world publish only papers. Okay, you need a matured industry ecosystem to take a paper published in Nature to convert it into a product or a technology. This job is unfair for a professor to expect to publish in a high impact journal and also develop a deployable product. It requires a matured industry ecosystem. Now, that matured industry ecosystem did not exist in the country, and therefore they could not take that research into a deployable technology, to develop the products or the technologies or something. But there is some silver lining in this, and that answers your questions of the mindset. What is happening is, and India is very, very uniquely positioned to say that we are the third largest startup ecosystem. It has not happened just like that. This is to harness our large, young, innovative populations. Okay, and it is these youngsters, it is these young students who are graduates. If they can spin off from the research and form the startups, and that is happening. That is happening. I mentioned that there are 10,000 deep tech startups, all founded by youngsters, and they can really develop cutting edge technology products which is globally competitive, but then they are not able to get the VC funding because these are, private investors have been so far risk averse. And this fund will actually be helpful to take that, mitigate that risks and that invite, and hopefully we are hoping that if this RDI funds takes up investing in some of these startups, maybe 10 years later we will have a company like an IBM or something like this. And once that kind of a ecosystem develops, even the private sector corporates also actually they will pitch in, because it is a question of creating a ecosystem. We had left it into an ecosystem where the industry was very happy to import the technology and develop the products. Academia were only publishing the papers, but the disruption that has happened in the last few years is of these entrepreneurial mindsets which has been coming up. So once you talk of the mindset of the industry, I think we have to focus on the entrepreneurial mindsets amongst our youngsters, and there is a need to harness that potential, because that has a great potential of making a quantum leap or taking that change. It is not possible to change the mindset of an industry that has been in existence for like 100 years, and it is so that is number one. Number two, also it is unfair to sort of expect an academia to develop a product. However, what we are saying, what we need is these translational research centers which will work with the academia, but not the professor. Don't expect the professors to develop the technology in his or her lab. We have these translational research labs which will work with this academia. Let that professors be on the board of startups, let them mentor, but someone else, the engineering talent and the engineers, and I'm hoping that these youngsters need to do that work of translating the research into this. And once you have a matured industry ecosystem, they will take a US patent filed by an academics and a high impact journal paper published to convert this into a deployable product. That's what is happening in other parts of the world. I mean, it is fashionable to say that Stanford University is developing technology, but the Stanford University professors, which all I know in our areas, in electrical engineering, in wireless communications and networkings, they only publish papers, but they work very closely with the industry. They don't develop the product. So I think that is really the change that we are seeing, and hopefully that will happen in the next few years.
Last question.
Yeah, so my question is on manpower. We see a lot of people moving to, for even undergraduate to the US and other places. So, I mean, earlier it was happening at a higher level. Now we see much younger people wanting to study abroad. So the talent is where I'm putting a question mark on, where the talent will come from. The second thing we are seeing is among the engineering disciplines, there is a lot more focus on computer science, so people want to take that. So, I mean, how do we need a lot of things that you said and the previous speaker said about developing hardcore engineering solutions. So where is the manpower for that going to come from?
No, I think as I had pointed out on the ANRF, 4 strategic interventions, and so 4 strategic interventions, as I mentioned, that capacity building and investing in research in state public universities and the university ecosystem and our other institutions is the only way to grow the R&D talent, and which is actually a very big issue. It is not just the funding, but the R&D talent is a very big issue. In fact, if you see the number of R&D personals in India is only about 260 per million, compared to even a small country like South Korea, where the R&D equivalent personnel is 3,000 per million. So that is really the difference. So it is not just the funding, but it is the talent. And I think this has been recognized that the talent creation, particularly in the core engineering discipline, is an important aspect. And once the industry ecosystem grows, we are hoping that that will also help in creating the talent, because those talents will also be needed in the technology sector. Yeah. Yes, yes.
Yeah. I have a very small question. I spent about 30 years in the university system. And my question is that when it comes to funding by DST or any other funding agency, somehow, somewhere, the university systems get ignored.
Yeah.
And the reason is always this: it's like a chicken egg problem. You do not have this much, so how can we fund you for this much more?
Yeah.
But that initial funding, unlike IITs where young faculty gets a lot of seed money, people who join universities, I was at the University of Delhi, which is better placed than other universities, but the seed funding is not there.
Yes.
Young faculty joins, has no money, in fact sometimes not
Yes.
even a table and chair to sit on to begin the career.
Yes, yes.
And then when they apply for little projects, small projects also to DST, the question is, you do not have this, and how can we give you this? You do not have this. So this 35 years, we did not draw too much funding in my department, which is Department of Electronic Science at South Campus. And even today, my young colleagues have not been able to draw money from there.
Yeah. So I think, let me just answer this. The pair program of the ANRF is exactly meant to address that gap. And we will now be funding, to the 45 public universities, and we are investing about 700 crores in that. So hopefully that will sort of synergize the seed funding, and ANRF actually that is going to do that. That is really one of the objectives. Now, having said this, all I can say is that, of course, I mean, you told the problem of Delhi University faculty not even getting a table and chair, but even in IIT you may get only table and chair. So that is also true, because the funding issues remain, and so therefore I think it is therefore really very, very important, because the government funding also has a limitation. What I'm saying is that it has a limitation, and unless we have a matured R&D ecosystem available in the research labs in the industry, we are not going to increase the quantum of funding available for both basic and applied research. But I think I take your point for the state public universities. Hopefully the pair program of the ANRF will address that.
Yeah, go ahead.
I think I need to sort of.
Thank you very much, Professor.
Thank you very much, sir, for that powerful and deeply insightful keynote address. We are sincerely grateful to you for taking time out of your incredibly busy schedule to be with us today. Now, may I request Dr. P.S. Goel, chair of the session, to kindly present a token of appreciation, a memento, to Professor Abhay Karandikar as a gesture of our heartfelt gratitude for his presence and inspiring keynote address. Thank you, sir. At the end, may I request Lieutenant Colonel Shobit Rai, officiating Executive Director INAE, to kindly propose the vote of thanks.
Esteemed dignitaries present here today, young students, faculty members, it's an honor for me to present the vote of thanks on behalf of the Academy. Firstly, let me express my gratitude to the chief guest of our function today, Professor Abhay Karandikar, Secretary to the Government of India, Department of Science and Technology, and our other esteemed invited speakers, Professor Surkole and Dr. Subramaniam, for their valuable insights presented during their valuable talks. I see our chief guest has hurried and I thank him before he leaves. Thank you, sir. My gratitude to the former presidents of INA, Dr. Goyal, Dr. Mishra, Professor Manna, being present here today. President INA, Mr. Patil, and our vice presidents, governing council members, esteemed fellows, learned faculty members from IIT Delhi, other invited guests, INA's young associates, members of INA, research scholars who are present here, and most important, students. For gracing this occasion today and being present here today, a Sunday well spent. I am grateful to Professor Rangan Banerjee, Director IIT Delhi, Professor Santanu Chaudhary, Vice President INA, Professor Gandhi for all the help extended in organizing this function at IIT Delhi. I also remain in gratitude to our team in INA, not only for today, but their steadfast commitment to see that we excel under the guidance of INA's leadership. The inaugural issue of the e-magazine released today, Tech Frontier, shall be made available on INA's website today and will be mailed to all our esteemed invitees. With this, I now request our esteemed speakers, presidents, INA, former presidents, vice presidents, to kindly come onto the dais for a quick photograph before we break for the lunch. Kindly be patient with us for a couple of minutes. We will proceed for lunch after this. May I invite?
बंद तो नहीं कर दिया प्रोजेक्टर बंद कर दिया यार प्रोजेक्टर बंद कर दिया यार पीछे डाल देंगे बंद कर दिया प्रोजेक्टर सर आप खिंचवा लीजिए पिक्चर
Thank you, ladies and gentlemen. We can now proceed for the lunch. Thank you very much. Grateful.